The test that you just saw is an example of one kind of non-parametric test. Category of tests that we're going to talk about here is non-parametric tests. The tests that you probably have seen in previous statistics courses are most likely called parametric tests, something like a t-test, which is the kind of test we'll see as we go forward here. T-tests and other parametric tests involve parameters, Greek letters like mu. There are no Greek letters in what I just did, right, with the little HLab example. In general, what characterizes non-parametric tests is a lack of parameters, a lack of Greek letters, but also in general, a lack of assumptions. These tend to be a class of tests that work very well, even when the assumptions that you would need to make to do other alternative tests would not be true. The particular type of test that we just carried out is called a randomization test, which seems like an appropriate name because what we did is we looked at all the different ways the randomization of units to treatment versus control could have come out, right? We made a list of all the different possible ways. And in that study, the units actually were randomized to offers of HLab help versus not. Another name that is usually used interchangeably with randomization test is permutation test. So permutation is a way to mix up a bunch of values, basically. And so you can see that the test that you just saw looked at all the different ways to permute the T's and the C's, right? So often these terms, randomization test and permutation test, are used interchangeably. So I'm going to write permutation test is equivalent. However, there's one textbook that I like to use sometimes called The Statistical Sleuth by Ramsey and Schaefer. And they actually distinguish between these two terms in a way that I think is sometimes helpful, at least to think about at this moment. So in that book, there's only one procedure, right? You can follow the steps we just followed. But when you do it, you either call it a randomization test or a permutation test. Those authors suggest calling it a randomization test if somebody actually randomized. So in the HLab study, we actually flipped coins to determine who was going to be offered help from HLab versus not. And so those different sequences of T's and C's actually could have occurred, right? But suppose that instead I was trying to look at some data, maybe the outcome variable is whether you're employed at a certain age, maybe age 30, and maybe the two groups are whether you went to college versus not. Now, this is not actually a randomized study, right? Nobody randomized whether a particular person went to college or not. But you could totally imagine carrying out the same procedure, right? Listing maybe a T if somebody went to college and a C if they didn't go to college, and you could carry out the same steps. The null hypothesis would be that there's no relationship between whether you went to college and whether you're employed at age 30. And so what I'm saying here is that you can carry out the same steps we just carried out, even if you didn't actually randomize. And it can sometimes be helpful to, in your mind, call that a permutation test rather than use the word randomization, since nobody actually randomized. But regardless of whether somebody actually randomized or not, carrying out the steps that we just carried out to generate a p-value is called a randomization or permutation test. There are some benefits of this class of tests. They are useful for any sampling scheme. So we've already just done it for simple random sampling and for Bernoulli, but if you knew you had sequential sampling or stratified sampling, any kind of sampling method, you could have listed out all the T's, all the sequences of T's and C's that were actually possible, given whatever the scheme was, right? And you could have carried out the steps. And so that is a flexibility built into this kind of test that does not exist in something like a t-test, where you have to assume a particular sampling scheme. Another little bit of flexibility here, actually it's a lot of flexibility, is that you could use any test statistic. So I used a difference in mean win rates, but I didn't have to, right? Suppose that we weren't interested in a 0-1 outcome like win rate, but instead we're interested in a numeric outcome, like how long did it take to resolve somebody's case, right? Instead of looking at the mean in each group and taking the difference, I could have found the median of the outcome among those who got T versus those who got C and subtracted, or even taken the ratio, right? As we move forward, you'll see some examples of other test statistics that could be used. And that's another flexibility that does not exist in other kinds of tests you may have seen before. If you're more interested in medians, you can do that here. Another benefit is this works for any sample size. Now, is it great to do a study with only 3 people in it? No, like don't do that, right? But there was no point at which I needed to assume that my sample size was large enough to continue. Unlike other tests that we're going to see, like t-tests, where you need to assume the sample size is big enough for some mathematical theories to hold. In addition, there's no distributional assumptions. At no point do we say, oh, I hope the data looks normal. We didn't have to check that. We didn't have to worry about that. So no distributional assumptions such as normality. Okay, so when you're thinking about doing any of the non-parametric tests, the one that I just showed you or the ones that are coming next, right? You can see the benefits include that this is so flexible. You don't have to assume that you have normality. Any sample size is fine. If you don't want to deal with means, deal with medians or something else. If you don't have simple random sampling, fine, no problem. Just make a list of all the different sequences of T's and C's that would have been possible. So to give you a sense of what's coming, we're going to talk about how to vary some of these different characteristics of the hypothesis test. So we are talking about how to vary. Well, we've already talked about how to vary the sampling scheme, right? We already talked about Bernoulli and simple random sampling. And then the one that's coming as we go forward in the material is paired data. You haven't seen that yet, okay? But we could also vary the test statistic. I just said that the test statistic is flexible. So we're going to talk about how to vary it. You just saw the difference in means. But we could also deal with medians. And we're also going to be introduced very soon to some other test statistics that can be helpful in certain cases. What else? In addition to listing out explicitly all the T's and C's, it turns out there's more than one way to generate that reference distribution and therefore the p-value. So another thing we're going to talk about how to vary is the ways to generate the reference distribution. Because so far, you've only seen what's called the exact way, but I bet it is clear to you that if we actually try to list out all the different sequences of T's and C's that are possible for a very large sample size, that gets really, really annoying, even if you are a computer. And so it turns out there are some really nice ways to get around listing out all the T's and C's and still complete the test and generate a p-value. So these bullet points here are a framework for how we're going to continue our discussion of non-parametric tests. We're going to think about what other sampling schemes we might have. Particularly, we'll talk about pairs, different test statistics, and different ways to generate the reference distribution. So you can see the full flexibility of how broad this class of techniques can be.